Hello, can you hear me?
Yeah, perfect.
Thanks to the organisers for an awesome workshop. I'm going to come away a lot, very inspired and enlightened. And today I'll be presenting work from friends and colleagues from COPE, the Centre for Organic Photonics and Electronics, and on a new electron acceptor solution processor. So just a brief outline. First I'll just briefly go over what we want in an acceptor material, and then introduce our new acceptor, and then talk about the morphology of this acceptor material and how it influences charge mobility and the cell performance. And there's the structure there, which I'll explain a bit later. So the ideal acceptor has complementary absorption to the donor material in order to maximize photocurrent, match electron affinity to the donor's ionization energy in the photoexcited state to maximize photovoltage. It's electron transporting, of course, we want to collect the charges, and we want to have a high dielectric constant to minimize recombination. And they're the champions we've seen throughout the week. But there's been other attempts at non-Fullerene acceptors, mostly paralleling and its derivatives, and it's resulted in efficiencies between 1% and 2%, wrong side. There's a handful of vinosines and their derivatives, and they've achieved about 1.1, 1.4%. And there's been polymeric acceptor materials, which are a bit higher performing, about 2%, and some diketone, pyrrole acceptors that have achieved about 1% of P2H2. So today I'm going to introduce our acceptor material, K12. K because it's the first name of the creator, Kurt Louis, in the audience. And it includes a electron donating fluorine group and the electron accepting benzothiazole and dicyclone groups, which results in a strong ground state dipole moment of about 9.2 Debye. And we can solution process it or vacuum deposit it, and with a bit of annealing we can get it to form these organised structures both from the vacuum deposited and solution processed films. And you can see here that there's some long-range order, which is reminiscent of a smectic type liquid crystal, although we're not entirely sure about this yet. So the optical properties, we see that there's some complementarity to the P2H2 absorption spectra, and it also shares quite a strong 0,0 vibronic band absorption edge compared with P2H2. So this is an indication of strong intermolecular interaction. The forbidden energy level diagram. Here we've got the electron affinity of our acceptor, about 3.6, which is a smidgen higher than PCBM, as measured by cyclic voltammetry, and the HOMO energy of about 6.2, which is right on the edge of that observed from photoelectron spectroscopy in air that Berendra explained earlier. The dielectric constant is about 3, not as high as PCBM, but nevertheless. And we expect electron and hole transfer. So the first thing you want to check with a new acceptor is whether or not the exciton separation rate is faster than the exciton recombination rate. And to do that, we blend small amounts of the acceptor with the P2H2, and we compare the photoluminescence quantum yield of the pristine with the blend, and we see that indeed K12 is quite a good electron acceptor, or at least a quencher. And compared with PCBM, I wouldn't say it's better because we know that PCBM aggregates even at such low concentrations, but this concentration here for our K12 is about 2% by weight. So it's not too bad, and this is kind of indicative of intercalation as well, the P2H2. So what about the transport properties? Well, it can carry electrons, which is good, as seen here in the time of flight transient. And we see a nice increase in the mobility upon crystallization of the film. So here's a as cast amorphous measure of mobility. And once we crystallise the film, here you can see the crystals between the ITO and the aluminium contact. We see a massive order of magnitude jump in the mobility. And with a bit of hard work, we can squeeze out about 10 to minus 3 in field effect and time of flight measurements. So how's it going? A device? Well, as Schwenn pointed out, bilayer is quite a facile route to making solid cells, and also helps isolate the acceptor metal interface. So we use this to find the right metals to use. It turned out calcium was good. It was the S-shaped curve mentioned earlier. And we also see that the annealing effect and the change in mobility also improves the bilayer device. So this suggests that, well, first of all, the efficiency goes from about 0.08, which is quite low, to 0.3, which is a bit better. And it follows the short circuit current, a bit of an increase in the open circuit and a decrease in the series resistance. So we attribute this increase in performance to the charge transport in the K12 layer. And because it's we can say this is more like a bilayer because we have quite a thick acceptor layer on top of P2HT. And the bilayer structure also helps minimise bimolecular recombination, but we still have germinal recombination, which could be a problem. So a closer look at the surface, we see that the as-cast amorphous film looks amorphous, but upon annealing, we see that there's this nice structured morphology, quite large, and so there's a clear structure function relationship with the mobility there. But if we tried to pull this annealing trick in a bulk heterojunction cell, it probably wouldn't work as well because there's such large phase separation. So before we move to that, we have to have a closer look at the thermal properties of the material. And we see that with differential scanning calorimetry, that there's this low temperature endothermic transition here, and then an exothermic, and then a larger endothermic transition, which then stabilizes the material as it cools down. So this acts as a guide for when we go to make a bulk heterojunction, so that we don't end up, we can use it to basically optimize our bulk heterojunction structure. And so now if we keep the cathode the same and then just go with a 1-to-1 by-weight blend using chlorobenzene, and look at the effect of annealing, we see that around this low temperature thermal transition, we see a massive jump in the efficiency. And we attribute this, of course, to the change in morphology of the K12 and of the K12 and its transport properties. So having a closer look at the EQE, we see that there's quite significant photocurrent coming from the absorption of our acceptor, which then makes P3HT the acceptor, but false. So, and we also are quite familiar with P3HT, and we can see that there's not much of a low energy absorption edge there. And so we normally improve that by thermally annealing P3HT. However, as we saw, high temperatures and our acceptor don't really, not very compatible because of large crystallization and phase separation. So we had to move to a solvent annealing approach in order to improve the P3HT crystallinity without causing massive phase separation of K12. And when we do that, we see a tiny little improvement in the red, which equates to about a 10% overall increase in the whole collection. So we can use this optimized processing conditions to then look at the effective blend ratio, and we find that the optimum blend ratio for P3HT and K12 is about 1:2. So despite all these optimizations, we end up with an efficiency of 0.73. So what's going wrong? It could be recombination, it could be transport. Can't really say much about recombination at this stage, but for transport, we can have a closer look at the K12 crystal structure. And when we do, we see that it's formed by these physical dimer pair, if you like, and we can draw a shortest path from through this stacked dimer. And so we can think of if electron has to flow through this crystal, it's going to be based on hops between the dimer or within the dimer, which is an intra-dimer hop, and a much longer inter-dimer hop. And we can do a bit of a back-of-the-envelope calculation of this using following the work of Schwenn and Brede. And that involves using the Einstein diffusion equation with the diffusion rate given by Marcus-Hush electron transfer rate equation in the high temperature limit. We can find this electron coupling term T just by taking the half of the LUMO level splitting of each dimer. And we can also calculate the reorganization energy for electron transfer doing the 4-point calculation mentioned earlier in the week. And we only take the internal part of this for simplicity. And we then add the transit times, which is the same as adding the mobilities in parallel. And we come up with a value of 5 to the minus 3, which agrees surprisingly well with the experiment. But this is the so this is the best possible transport we can get through the material. And as you see here, so this is with the greatest electronic coupling, and it's highly anisotropic. So basically any attempt to drive the electron in a different direction will result in a much lower mobility. So if we could magically remove the long hops and just make it all short hops, we end up with mobility comparable to PCBM, and we probably end up with a 5 or 6% cell. So we will introduce a new small molecule acceptor. It's a powerful quencher, has reasonable mobility. It has quite interesting self-assembly properties. We've achieved a power conversion efficiency of about 0.7 P2HT, and it's possible that transport anisotropy is the problem. I'd like to thank Kurt Louis, the creator of the molecule, and for doing the AFM, Paul Shaw for PLQI help, Carsten Kruger for time of flight CDF, Karen for FET measurements, Klein for FAB, Ben Powell for calculations, and Al Mentis and Scott Watkins for CDF and PISA, and funny bodies. Thanks a lot.
The results are really encouraging, given the fact that the new acceptor non-fullerene is very high mobility. Now we can think about actually all the donor molecules donor materials are optimized with respect to the fullerenes. And now we can think about optimizing the donors with respect to the new acceptor. So that's a really new revolution. So, and given the fact that so it's a very high mobility.
So you showed EQE data. Do you have any internal QE data?
No, not at this stage.
So it'd be interesting to see what's more efficient process.
Yeah, that's right. Yeah, that would be interesting.
Go ahead.
Oh, we have some preliminary microwave conductivity data which suggests that the charge generation rate may be about 0.4, but that's not based on optimized morphology also.
Unrelated question, sorry. What was the lambda in your Marcus-Hush theory?
It was about, from memory, I think it was 0.02 eV.
This is calculated.
Yeah. Okay. Maybe that was for the dimer, not for the interdimer. Interdimer was about order of magnitude less. So was it 0.2 or 0.02? Sorry.
If you could go back to that polarized microscopy image, was it between cross polarizers or parallel polarizers?
Cross polar.
You need to follow up on that.
Any insights?
Just to
semantic. What do you call geminate or what do you call bimolecular?
Um,
And how did you know that?
oh, and that's just inferred from the. Okay, so geminate is, I mean by from the same lexicon,
Okay.
and bimolecular is
Different.
yeah, different. Yeah.
And how did you determine this? Or how you?
Oh no, this is just an assumption based on the bilayer structure. So geminate recombination is likely to dominate because there's no intermingling of the phases through the K12 layer and the PQHT. So it's just a general assumption.
It's not from the light intensity.
No, we haven't.
Because it's very dangerous.
Yeah. No, it's just inferred from the geometry, that's all. Yeah.
So another question.
I have a little question. Did you check the stability of your K12 towards calcium?
I guess that would relate to overall stability of the device. It's not too bad, but it's definitely not entirely stable, the overall device performance. So that's possibly due, well, it's probably due to the strong self-organization of the acceptor, so the strong dipole. It's hard to isolate the two, whether or not the morphology is changing or whether or not it's reacting with the cathode.
Yeah, I'm asking that because I can imagine that it would form a kind of a salt.
Oh, okay.
I mean, if you look at the level of your LUMO, you would say, okay, it should be slightly less acceptor than PCBM, so it's fine. But I think that's a little bit too easy.
Yeah. Okay.
Could you tell me, do you have an idea where the blue peak of the K12 is shifted with respect to the IDC? It's quite a big difference between the two.
Why here?
Yeah, the constant two of that.
Oh, this one?
Yeah.
I think the glass attenuates the light a bit.
Oh, okay, sure.
I think.
Okay, if there's no more questions, let's thank our speaker again.